All right, everybody. So let's see. We left off here with the formula for computing a triple integral in cylindrical coordinates. And I think what is probably the most general case. So let's go to the first example. Let's let E be the region of space that is bounded below by the cone z equals to the square root of x squared plus y squared, and bounded above by the sphere x squared plus y squared plus z squared equals to 1. I think you'll recognize this as the unit sphere, right? Centered at the origin. And this cone is really kind of like the upper half of a cone. That's fine. I think we've seen this guy before. But let's see. Let's go to GeoGebra, I think. Right, we'll go to GeoGebra before we continue here. So let's see. Here we are. So let's type these in here in case you're wondering how to type something like the cone in. Z equals to, let's see here, we'll write SQRT, right? And then a parenthesis, and that'll make that turn into a little square root sign there. So then under there, we'll write x squared plus y squared. And that gives us this cone. Very nice. Okay. And let's also type in the sphere. X squared plus y squared plus z squared equals to 1. Alrighty. So we can see here now, in red is the sphere, and in blue is this cone. So let's kind of zoom in a little bit closer here. So it looks like the region of space that we care about is the region that it says bounded below by the cone. So the lower bound for z is going to be given to us by this cone. Z equals to the square root of x squared plus y squared. And it says bounded above by the sphere. So the upper bound, the upper part, z-wise, is going to be this sphere. So we might end up taking this equation for the sphere and solving for z. We really only need the upper half, the upper hemisphere. So we might do that in a minute. But notice here that if we kind of turn this around, that it looks like that this shape, this region of space, this kind of ice cream cone sort of region, has rotational symmetry around the z-axis, right? The blue axis there. So, so we'd like to choose cylindrical coordinates where z equals to z and the xy plane is modeled by polar coordinates. So if we do that, it's pretty clear from the picture here that the lower bound for z is this equation of this cone, and the upper bound for z is the equation of this sphere once we just solve for z and just get the top half. So then once we've taken care of that, once we've got that z bound sorted out, the next thing to do is sort of project the shape to the xy plane, which for our purposes here in GeoGebra is we'll just kind of stare at this shape from the sort of looking down the barrel of the z-axis, right? And what do you see when you project this shape to the xy plane? I see this circle here, right? This red circle. That looks like actually kind of the circle of intersection between the sphere and the cone, right? Just imagine that as just sitting in the xy plane at z equals 0. So this will be the polar region D, right? Over which we'll do then a double integral after we sorted out our z integral. So we'd like to know, it looks like theta will go all the way around from 0 to 2 pi. But we'd like to know the radius of this circle here. So perhaps we'd like to first write everything that we have in terms of cylindrical coordinates, and then see if we can't maybe solve and figure out what the radius of that intersection is. So let's scoot back over here to the slideshow and see what's going on. So we've looked at the picture in GeoGebra, and we've decided to use cylindrical coordinates r, theta, z, because there was rotational symmetry about the z-axis. So let's go to the cone here. The cone is z equals to the square root of x squared plus y squared. Well, remember, in polar coordinates for x and y, x squared plus y squared is r squared. And the square root of r squared should just be r. So we get this very nice equation for the cone in cylindrical coordinates, that z equals to r. That's very nice. It's like a linear function of r, right? Very nice. Okay, the sphere x squared plus y squared plus z squared equals 1, well, that condenses to just r squared plus z squared equals 1 for the same reason that the cone did. So let's solve for the upper hemisphere now, right? Just take z equals to the square root of 1 minus r squared. So if we want to find that circle of intersection between the cone and the northern hemisphere of the sphere there, we'll just set these two z's equal to each other. So we have r equals to the square root of 1 minus r squared. Then we can just square both sides. We'll have r squared is 1 minus r squared. Then add r squared to both sides. Then divide by 2. We get what? R squared equals 1/2, and then r equals to 1 over the square root of 2. So that circle of intersection between the cone and the northern hemisphere is a circle of radius 1 over the square root of 2. Okay. So let's go to do this integral now. We're going to find the volume. So remember, maybe I didn't say that yet. So, okay. So we'll compute the volume. Okay, so what we'll do to compute the volume is integrate the constant function f of x, y, z equals to 1 over this region E. Remember, that same fact that was true about double integrals in area is going to be true about triple integrals in volume. If we want to compute the volume, we'll triple integrate the function 1 over this region of space. So we can set up, we had our z-bounds. Our lower z-bound was the cone, z equals to r. And our upper z-bound is the northern hemisphere of that sphere. That was z equals to the square root of 1 minus r squared. And then the region of the xy plane over which this projected to was the circle centered at the origin of radius 1 over the square root of 2. So actually, it's like the whole disk there, actually. So r goes from 0 to 1 over the square root of 2. And theta goes from 0 to 2 pi. And again, we're going to integrate the constant function 1, but because we've done this pullback to cylindrical coordinates, we need to multiply our integrand by the Jacobian determinant, r. Okay, so here we go. The z integral is not so bad, right? We just slap a z on it, and then we get, we'll evaluate that at z is the square root of 1 minus r squared, and z equals r, and take the difference. And so now we're going to do a double integral over the disk of radius 1 over the square root 2 of the function r times the square root of 1 minus r squared minus r squared. So it looks like we can break these into two because I think the second one is just a routine integral and the first one seems to be screaming out to us that it is u substitution. So we will do some u substitution on the first one. We'll let u equal 1 minus r squared. So then du is negative 2r dr. And if we're going to change that integral into the u close, we're going to need to change the bounds, right? So we'll evaluate u of 0 is 1 minus 0, which is just 1. And u of 1 over the square root of 2 is 1 minus a half, right? Which is a half. So then the first of those two integrals looks like this. It's the integral from 0 to 2 pi of the integral from 1 to a half of negative a half the square root of u du, where this a half here comes from the fact that we have to cancel out. In fact, this negative a half comes from the fact that we have to cancel out negative 2 in du. So that's good. And the second of those integrals remains as it was before. It's just routine, so we'll worry about it in a second. One thing I noticed on this first one, though, is that we're integrating backwards, right? We don't like to do that, so we'll switch our bounds so that the lower one is truly lower. And by doing that, we also negate this minus sign, so that's beautiful. Okay, and then what is this integral? Like, the square root of u is u to the 1/2, right? So the backwards power rule tells us that the integral becomes something like u to the 3/2 times 2/3. So, so when we multiply that by a half, we should get 1/3 coming out to the front. But that's fine. So now we'll have u to the 3/2, which will evaluate at 1 and at 1/2 and take the difference. The second of those two integrals we can now evaluate now that we're ready to do the first one, I guess. it was just r squared, it becomes 1/3 r cubed. And we'll evaluate that one at r equals 1 over the square root of 2 and r equals 0 and take the difference. So then what do we get here? You can yank out a third, right? Because a half times 2/3 is just 1/3. I'll yank that out, and I'll evaluate u to the 3/2 at 1. That gives me just 1. And 1/2 to the 3/2, well, that's like 1 over the square root of 2 cubed, which is 1 over 2 times the square root of 2. Okay? And actually, oops, sorry. So actually, that same computation holds true again. We have 1/3, which we yank out for the second integral, and 1 over the square root of 2 cubed is still 1 over 2 square roots of 2. So now we have 1/3 out front of everything, and we're going to integrate from 0 to 2 pi, right? And with respect to theta. And I don't see any thetas in either of these expressions that we're integrating. So we're really just going to multiply both of these numbers by 2 pi at the end of the day. So we'll just multiply everything by 2 pi. And what do we get? 2 pi over 3, that's the 1/3 being factored out there, times, let's see, we have 1 minus 1 over 2 square roots of 2 minus another 1 over 2 square roots of 2. That gives us just 1 over just the square root of 2. So that's this computation. I think we're done here then. So join us again in the next video. We'll do another example here that maybe is a little bit weirder. So see you then.